Okay, hello again. So we're up to chapter 8, so subnetting of IP networks. Yeah, this is probably the hardest chapter in CCNA 1. Okay, we're going to look at subnetting with an IPv4 network. So we'll look at implementing an IPv4 addressing scheme to enable end-to-end connectivity in a small, medium-sized business network. So we'll look at how subnetting segments a network to enable better communication. And so we'll look at calculating subnets for /24 as also /16s and /8s. Given a set of requirements for subnetting, implement an addressing scheme, and we'll explain how to create an addressing scheme using variable length subnet masking, or VLSM. We'll also look at addressing schemes, and so given a set of requirements, we'll implement a VLSM addressing scheme to provide connectivity to end users in a small, medium-sized network. So we'll implement a VLSM addressing scheme. And we will look at IPv6 as well, but the complications in IPv6 are much less because there's a lot more space, and so it's very simple. Okay, so subnetting IPv4 address. So basically, many devices use broadcasts on Ethernet LANs to locate other devices or services. And so, for other devices, they'll use things like ARP. And so broadcasts actually chew up resources on computers as well as networks. And so basically, for every broadcast, every computer will actually receive that frame. The NIC will look at it and go, well, it's a broadcast, I need to send it up to layer 3. And the layer 3, if it's still a broadcast destination, will actually have to ask layer 4 if it's interested in it. And so as soon as you get into layer 3, it's in software, it's in RAM, it's using the CPU, and so it actually does use a fair few resources. And so with IPv6, of course, they don't do broadcasts, and the NICs can actually filter out multicast that they are and aren't interested in. With broadcasts, it's not as easy to do, and so it takes more effort to do, and it does take RAM and CPU effort to do it. So if you divide networks into smaller networks, multiple smaller networks, and then less hosts, there's actually less broadcasts on a network, and so that does make things a lot more efficient. So switches always forward broadcasts, routers do not, and so basically the more router ports you have, the more things that are blocking broadcasts, and so it makes the network more efficient. And so the larger the network, the more the hosts, the more the broadcasts, and so much of the bandwidth is taken up on just broadcast that actual moving the data you wish to move gets more and more problematic. And so if you reduce the size of a broadcast domain and make multiple smaller broadcast domains, it actually makes things a lot more efficient. Same as so basically the smaller the broadcast domain, the better it is. Okay, so the reasons we do it is reduce the overall network traffic and improves network performance. Also, it enables an administrator to implement security policies such as which subnets are allowed to communicate with other subnets. And so each router interface can have an access control list applied to it. And so if you've got these different ones, you can differentiate the traffic between different departments a lot easier. And so you can actually implement security a lot easier as well. And of course, the less broadcasts also makes it less more secure, because broadcasts, of course, everyone sees, and so that's a way that if someone's somehow infiltrated a PC inside your network, they'll actually get less information as well. So it's all good for security. Okay. Subnetting on octet boundaries is very neat and very easy, but not always practical. So basically, there's only 3 subnets masks you can use on the octet boundaries, and of course they're the classic A, B, and C class masks: /8, /16, and /24. So of course a C class you can't subnet further and do it on the octet boundary, so you're going to have to look at a B or an A class to be able to do that. And so because with the C, of course, we've already used the last octet boundary, and so you've got to chop up that last octet. If you've got a 10 network that you're subnetting within your organization, of course, it gives you lots of options. You've got 24 bits that you can play with, and so you can create lots of subnets, or you can create very big subnets, or whatever your needs are. But yeah, B's are of course halfway in between, and C, a lot less options because you've got a lot less host numbers, as you can see from the table. Okay, so subnetting at octet boundary, basically, as I said, if you've got that 10 network, as I was talking about, instead of a /8, you can subnet it as a /16, and so that suddenly gives you 65,000 possible addresses on each subnet, which is lots. And of course, it gives you 256 possible subnets as well. So that's tons. And so basically, yeah, lots of options, and of course, it's free. Of course, you can also subnet with a /24 as opposed to this was a /16 here. This one is a /24, and so the difference is there. You can have 65,000 subnets, each with 254 hosts, and so that's another option. If you need more than 256 subnets, well, there, the 10 network gives you that. Of course, those two broad brush strokes may not suit your needs. You might need more than 254 hosts per subnet, or you might need more than 256 subnets, and so you can sort of play around somewhere in the middle. And so, of course, here we're subnetting a /24 network, and so of course, basically /24 is the shortest mask you can have, but of course you can go all the way up to for a C-class address to a /30 as well. So it gives you at least 1, 2, 3, 4, 5, 6, 7 options for subnetting. Now, basically, when you design your addressing scheme, you've got to come up with what your needs are. You've got to discover what the needs are and then try and meet them with the addressing scheme. And so basically, if you only need 2 subnets, you only need to borrow 1 bit with a /24. And so you would actually borrow that 1 bit from the host section, has to be the first bit, of course, and then add that to the network portion. And so that will give you 25 bits of network number, 7 bits of host number, and so that will actually get you 2 subnets. So you've got 2 options with 1 bit, 0 and 1. And so from there, you've actually got 7 bits left. So 2 to the power of 7 is 128, minus the 2 unusable addresses. You can actually have 126 hosts per subnet. And so that is certainly a viable option. 100 hosts in a subnet is, reasonable. And so, of course, your mask would need to change in simple CIDR notation or network prefix notation. All you'd need to do is, instead of /24, this is now /25. With a subnet mask, of course, it would end up being 255, 255, 255, and of course the column value for the first bit in the 8th octet is fourth octet is 128, so that mask would actually be 128. 128 or /25, basically, yeah. So that is certainly a viable option. And so how do we create those subnets? Well, basically, we need to define it on the router interfaces. And so in this case, they've done the first subnet for Ethernet gigabit 00 and the second subnet for gigabit Ethernet 1. Now, of course, if we go back to this previous page, you've got a 0 in that bit, so the network number is still going to be 0. With a 1 in that bit, that's the other option, of course, the network number is going to be 128. And so basically, with the first subnet, you've got a host range of, well, you've got the network number of 0, then you've got the host address of 1 through to 126. 127, of course, would be all of those bits being set to 1, that would be the directed broadcast for the subnet. And then, of course, then the next number is 1, and so that gets you into the next subnet. So the subnet number is 128. So again, you've got the 7 bits, and so 128 is the network number, 129 would be the first host, 130, carry on up until 254 would be the last host, and then 255 would be the directed broadcast for that subnet. And so that's the basic behind it all. So if we go back to this, that's what they've done here, is they've used the first host number in the first subnet, of course, for the router G00, and they've used the first IP address in the second subnet, which is 129, for the router again on G01. And you can see the subnet mask has been changed to that 255.255.255.128. And of course on a host, in this case, this is the second host number on the second subnet, so 192.168.1.130. So it's going to be in the same subnet as that. It's got the same mask, and of course the gateway is that address there. And so that's basically defined this host and this. No, okay, this is just the subnet number, it's not the switch IP address. So of course that's the host number is 129 there, it's 130 there, it's 1 there, and it's 2 there. So that's the first host of the first subnet. Well, sorry, first host, second host. Now, there are formula that we use to calculate how many subnets we create. And so, of course, the previous example, we borrowed 1 bit. So 2 to the power of 1 is itself. And so we created 2 subnets. So n is the number of bits we're borrowing. And so if we borrow 2 bits, it's 2 to the power of n. So 2 to the power of 2, we get 4 subnets. And so 3 will be 8, and 4, and so on, and so on, and so on. So as you can see here, we can create 2 subnets, 4, 8, 16, 32, and 64. This is all with a /24. Now, okay, so obviously you've seen a different slide set before, but anyway, so the calculating the number of hosts on a subnet is basically how many host bits do you have left, and that's the number n that we're using. So it's 2 to the power of n minus 2. So remember, there's the subnet address you can't use, and then there's the subnet's broadcast address you can't use, and so that's the minus 2. And so in this case, we've got 7 bits. 2 to the power of 7 is 128. Minus 2, it means you've got 126 hosts per subnet. That's from that first example we had. Now, /26. So basically, instead of a /25, borrowing 1 bit, we're borrowing 2 bits from the 4th octet. And so with 2 bits, as I said before, 2 to the power of 2, we've got 4 subnets. And so we've got 0, 0, 0, 1, 1, 0, and 1, 1. And so basically we've got subnet 0, 64, 128, 192. If you can see a pattern, basically each of these numbers is jumping by 64. And if we look at the column values, guess what? That column value of the second bit that we've borrowed is 64. And so that's how your subnet numbers climb. If you looked at the previous one, of course, there was only 1 bit, and that column value was 128, and so you had 0 and 128. The numbers jump by 128. So there are whole polar patterns that once you get used to it, you'll actually not have to do these conversions into binary, but basically when you're starting out, using binary is the sensible way to go to make less errors. And so of course, when we borrow 2 bits, it means there's less bits available for the host section. And so there's 6 bits left. 2 to the power of 6 is 64. Minus 2, and so you get 62 hosts per subnet. And so again, 64, 64, it's giving you lots of hints here. And so here, of course, we can have 4 subnets. And so this is the first subnet here, .1. And then, of course, you know, the network number is 10, and then we've got 164 as the second subnet, and so the first host number is 65. 66, of course, is the second host number, and then we've got another subnet here, 128. So 129 and 130 are using this link. Now, this is traditional subnetting, where every subnet has the same mask, and so this is a little inefficient. We've got 62 available addresses, but we're only using 2, so 60 are going to waste. So when we talk about BLSM a bit later, that's actually serial links is one of them, where we actually save a lot of network addresses by having a very, very small subnet that we can use. But that's later. Okay, so when we create those 4 subnets, we're only seeing the top part of the table. The 4th subnet, well, net 3 is not visible. So again, all zeros in the host section. Of course, this is the first subnet, so the subnet portion is also zeros. So the network number is 192.168.1.0. First host, add 1 to that. And there's all the hosts in between until 62, as that's all 1s except for the last one is a 0. And then, of course, the broadcast for the subnet is that, which is 63. 64 is the next subnet, because it's 0, 1 there, all zeros in the host section. Then again, you've got 62 possible host numbers from 65 through to 126, and then you've got your broadcast. So it all follows the same pattern, and so basically each of these subnets has their own ranges. Okay, so how do you define that on the router? Well, again, the host address plus the mask, and so we've got a mask that's 255.255.192, which of course is the first 2 bits in the 4th octet. 128 plus 64 equals 192, so your mask is that bit, 1 bit longer again than the previous one. And so again, .1, .65, .129, they're your 3 subnets that have been defined on this router. Okay, now working with /16s, of course, you've got a lot more space, and so again, you've got a lot more options, and so you have the option of just being a bit lazy and I suppose less error prone, and you can, of course, choose the octet boundary, so you can have 256 subnets with 254 hosts per subnet. That is certainly an option, but of course, that may not suit, and so you've got all these other options as well. You can borrow anywhere from 1 bit through to 14 bits, and so lots of options. So as I said, 1 bit through to 14 bits, and so 1 bit gives you 2 networks with 1, 2, 3, 4, 5, 6, 7 plus 8, 2 to the power of 15, big number, several thousand. And so basically, you've got all those options, and so yeah, it's really, again, as I said, as your needs require. So again, calculating the number of hosts. In this instance, we've borrowed 7 bits. Well, that was the second half of this slide, was it? So we're using a /23 network, which is borrowing 7 bits. This is this one here. And so we've got 128 possible subnets, each with 8, 9 host bits per subnet. And so basically 2 to the power of 9, well, 2 to the power of 8 is 256, 2 to the power of 9 is double that, so 512 minus 2, 510 hosts per subnet. So that's a pretty decent subnet. And so again, gives you a lot of options. You can create, if you're using /8, again, you have lots of options because you've got 24 bits to play with. And so if you want to have subnets with 1,000 hosts each, 1,000 subnets, sorry, how many bits do you need to count to 1,000? And so, well, 512 was with 7 bits, so 8 bits you need to borrow. And so the second octet in total and the first 2 bits of the third octet. And so that would give you 1,024 subnets. Of course, you've got 8, 12, 14 bits remaining for your host section. So 2 to the power of 14, of course, gives you 16,382 possible hosts per subnet. So it's a very big subnet. That's a lot of growth. So basically, there's 2 ways you can subnet well, two ways you can come at a design is how many hosts you need per subnet, or the other one is how many subnets do you need to create, or a combination of the two. And so basically, you need to have a number of hosts that you need, and then you design the subnet mask to suit. And so basically, with a host requirement, you decide how many bits you're going to leave in the host number. And so in this case, we're leaving 7, so there's 126 possible hosts. When we leave 6, there's 62, and so on and so on and so on. Of course, another option is how many networks do we need to create? As I said, host devices used by employees in the engineering department in one network and management in a separate network. So basically, you know, you might have separate departments. They don't necessarily communicate 100% at least. You know, research and development might be very much separated from the rest of the network or something like that. So a network requirement example is how many networks do we need? So 1, 2, 3, 4, 5 subnets there, plus we'll have links. So that's actually 9 networks we'll need. And so what number are we using? And so here we're borrowing 4 bits from the host portion to create subnets. So 4 bits, 2 to the power of 4 is 16. So they need 16 networks. Of course, if you borrowed 3, you'd be able to create 8 subnets. And as I said, you probably need 9. And so that's why they've had to borrow 4. And so, of course, we've got why is this host? Oh, okay. So we've borrowed 4 bits. 1, 2, 3, 4, 5, 6. I have no clue what this I'm talking about here. They've got network portion, host portion. Anyway, and so as I said, you've got 9 subnets you create. They're all /26, and so that allows you to subnet the network. And so this is traditional subnetting where all networks get the same subnet mask. As I said, it gets quite wasteful. These links only need 2, but if they're getting 60 odd, that's not ideal. And so you can actually be a lot more efficient, and so it allows you to leave more addressing for the LANs, and you need less for the WANs, and so that's certainly a better solution. So basically, VLSM or variable length subnet mask means each subnet can have a subnet mask that suits their needs. And so in this case, traditionally you would have had to create for 30 hosts per subnet. You can create 8 subnets. That's not enough. If that's not enough, that's not enough. But if you need 30 hosts per subnet, well then you're running out of space. And so with VLSM, so maybe you can have 7 host subnets with 30 hosts, and then you can divide that last 8 subnet up to be used for those point-to-point links or something like that. And so so that certainly does make things a lot more flexible. So basic VLSM is we had those 8 from 0 through to 7th subnets, and then this last one we actually then split it up into the /30s for the point-to-point links. And so on router 2, which is here, we define the subnet for those networks that need 30 hosts there with that 224. And then here, with the serial links going on either side, they only need 2, so they've got the /30 there. And so a lot more efficient way of doing things. So I will actually do a demo later, and we'll work through some of these issues. So basically, we're subnetting a subnet. And so we've got the WAN links between R1 and R2, R2 and R3, and R3 and R4. And they're what we used out of that last one. And there's actually some spare 1, 2, 3, 4, 5 subnets that we haven't used yet. So yeah, very convenient. So addressing schemes. So planning requires decisions in each subnet in terms of size, number of hosts per subnet, and how many host addresses will be assigned. So you've got to do some investigation and some planning on what's required. So of course, with addressing schemes, you've got to try and prevent duplicate addresses because those hosts won't be able to work. And of course, you need to be able to monitor security and performance and provide control of access. And so each host in an internetwork must have a unique address, need proper planning and documentation, must provide and control access to servers from internal hosts and external hosts. Layer 3 static addresses assigned to a server can be used to control access to that server. Monitoring security and performance of hosts means network traffic is examined for source IP addresses that are generating or receiving excessive packets. Now, how do we assign these addresses? Now, of course, for hosts, normal client machines, you would normally use DHCP. With servers, often they would be statically assigned, or at least a fixed IP address. Intermediary devices, so routers and switches, again, they would be static addresses typically. And of course, you've got the gateway, which is used to route between networks. Now, IPv6. IPv6 subnetting is not concerned with conserving address space. There is so much address space. IPv6 subnetting is about building an address hierarchy based on the number of subnetworks needed. IPv6 linked local addresses are never subnetted because they're not used between networks. IPv6 global unicast addresses can be subnetted. Now, as we said in this previous chapter, when you get an IPv6 address from a network information center, you actually normally get a /48 address, and so that gives you the 16 bits free. So that allows you to create 2 to the power of 16, 65,536 subnets. So that's very, very flexible for you. And so you don't need to borrow host bits in this because they've actually given you spare network bits. And so it's very, very convenient. So basically, as I said, the last 16 bits of the network address, you can cycle from 0 through to all Fs, and then, as I said, 65,536 possible subnets. So basically, from there, this is the number we've gotten from the NIC, and then you can just cycle from 1 through to however many you need. And so, very convenient way of doing these things. And so, of course, that's how you type it into a router. Okay, that's it for the chapter. And so there are some activities for the 2 chapters. Now, a lot of it is sort of, again, more conceptual than anything. But I will actually do a demo on how we do the subnetting, and I'll actually show you how to assign IP addresses and IPv6 addresses in a demo that will be available shortly. So have a nice day. There's the logo.